Welcome to a fresh deep dive, where we really try to extract the critical insights from the latest research.
That's the plan.
Today, we're zeroing in on that hidden world inside machinery. Specifically, how we can spot these subtle electrical issues, before they turn into major headaches.
Yeah, it's all about catching things early. Our focus is on electrical insulation health and those precursors to damage. Sneaky stuff.
Exactly. We've got a stack of sources here, mostly research papers looking at electrical and current signature analysis, ESA and MCSA.
Right, and also a really interesting look into Supra Harmonics, which are becoming, increasingly important.
So our mission today, cut through the jargon, get a handle on how these tools, ESA and MCSA, act as an early warning system. For all sorts of machinery problems. We want to prevent those costly failures, minimize downtime, especially in complex systems like wind turbines or anything running off a VFD.
Variable frequency drives, yeah.
Ultimately, how can we hear these problems inside the machines before we actually see them fail?
Think of this as your shortcut, your express lane, to understanding what can seem like a pretty dense field.
Okay.
We're pulling out the essentials from these technical papers to give you a clearer picture of how it works and why it matters more and more.
All right, let's unpack it. Starting with the foundations. Electrical and current signature analysis. ESA and MCSA. In simple terms, what are they actually giving us?
Well, at their core, they're like taking a really detailed electrical fingerprint of a machine while it's running.
A fingerprint, okay.
Yeah, by looking closely at the voltage and current signals, we can spot these tiny anomalies, red flags for potential problems. It's a bit like a doctor listening to a heartbeat, looking for irregularities.
Okay, so how are they different? ESA versus MCSA.
Good question. ESA is generally broader. It looks at all three phases of both voltage and current. It gives you a really comprehensive picture.
Right.
MCSA, on the other hand, tends to focus mainly on the current, maybe in just one or more phases.
So ESA is more holistic.
You could say that, yeah, more holistic. MCSA can be more targeted, perhaps for specific checks.
And where did these ideas come from? What's the history here?
Well, MCSA really emerged back in the 80s. The initial focus was on testing electric motor rotors, assessing their condition.
Okay.
ESA, which sometimes got called MCSA in the early days too, confusingly, that was developed around the same time by Oak Ridge National Labs.
Ah, Oak Ridge?
Yeah. Their scope was wider from the start, looking at bearings, gears, other electrical bits, mechanical bits, especially in things like motor-operated valves.
And I remember reading early on, people thought these methods could directly spot winding shorts. Is that right?
That's right. Yeah. William Thomson first flagged a specific signature thought to be winding shorts, but later research clarified it. It's actually more an indicator of winding stress.
Stress, not a direct short.
Exactly. Electrical energy between the turns in a coil. Now, high stress isn't a short, but it can definitely lead to insulation breaking down, eventual failure, especially as you mentioned with VFDs involved.
Okay. Now, a key part of this is looking at frequency spectra. What are we actually seeing there?
Right, the spectra. Basically, how a machine is running smoothly or with a problem creates unique patterns, peaks at different frequencies. The main signal is the carrier frequency, your basic AC line frequency, like 60 hertz here.
Yep.
When something's wrong, it often shows up as smaller peaks, kind of like little hills on either side of that main frequency. We call those sidebands.
Sidebands.
Yeah. Think of the main frequency as the machine's normal hum, and the sidebands are like faint whispers telling you if something's starting to go wrong.
The research mentions specific tools. Framatome EMPATH for ESA, MotorDoc EMPOWER for MCSA. Are there differences in how they collect the data?
Yeah, there are. They use different sampling rates, which affects the maximum frequency they can analyze the Fmax.
Oh, okay.
The EMPATH ESA system, it samples at 12 kilohertz, so its Fmax is 6 kilohertz.
Right.
The EMPOWER MCSA system samples much faster, 44.1 kilohertz. That gives it an Fmax of 22 kilohertz.
Wow, much higher.
Exactly. And that higher range becomes really important when we start talking about Supra Harmonics later on. It lets us hear those higher-pitched electrical signals, essentially.
And decibels, DB. Why use decibels for this analysis?
Decibels are great because they give us values that are load-independent and repeatable.
Load-independent, okay.
How? Instead of just raw signal size, which can change with load, dB gives a relative measure. It's calculated. The formula is 20 times the log base 10 of the defect current divided by the line frequency current, IDIF.
Got it.
So this lets us reliably compare data taken at different times, different operating conditions. It's like having a consistent yardstick for machine health, regardless of how hard it's working at that moment.
Makes sense. And finally, for the basics, knowing the machine's speed seems crucial.
Oh, absolutely critical. You need the running speed and the pole pass frequency PPF.
PPF.
Yeah, it's mathematically tied to the motor's poles and its operating slip. Identifying these is key because mechanical characteristics create specific peaks in the spectra. Trained analysts know what to look for.
Like a signature.
Exactly. Imagine a slightly wobbly wheel. The PPF is like feeling that thump each rotation. Changes there point to mechanical issues, but you see them in the electrical signature.
Okay, great foundation. So we have this electrical fingerprint. We analyze frequencies, measure anomalies in dB. How does this help specifically with electrical insulation problems?
Right. Insulation. ESA and MCSA can spot both direct breakdowns and, importantly, the conditions leading to breakdown.
Both direct and inferred.
Precisely. So in the current spectrum, you can see signatures for things like inner turn defects within a coil, physical movement of coils, issues in the rotor windings, even things related to the stator slots. They all leave unique spectral marks.
And does the size of that mark, the dB level, tell you how bad it is?
Generally, yes. The higher the dB level of a specific defect signature compared to the normal background noise, the more severe the condition is likely to be.
So it's quantifiable.
It gives you a quantitative idea, yeah. Not just, is there a problem?
Sure.
But potentially, how significant is this problem?
Are there general dB thresholds that signal, uh-oh?
Yeah, there are rules of thumb. If a defect signature pops up more than, say, 5 dB above the usual noise floor,
5 dB.
Or if it's below about -70 dB, when the noise floor itself averages around -85 dB, specifically for things like stator slot signatures and winding stress that's usually considered significant, worth looking into further.
It sounds like getting good data is important here, requires some care.
Absolutely. You need enough data collection time and the right sample rate to get good frequency resolution.
Resolution meaning?
Meaning you can clearly distinguish between frequencies that are very close together. The research mentioned, for instance, collecting ESA data for about 48 seconds gives you a resolution of 0.02 hertz.
Wow, very fine.
Yeah, and that can be crucial to tell different potential problems apart.
What if the insulation completely breaks down? Insulation to ground fault. How does that show up?
Interestingly, a major ground fault can actually show up in the analysis of the ground conductor itself.
On the ground wire.
Yeah. In bad cases, the frequency spectrum you see on the ground can almost mirror the mainline frequency spectrum. And usually you'll see higher leakage current flowing to ground too.
The papers also mentioned sidebands at ±15 hertz, around the line frequency.
Yeah.
What's the significance there?
Ah, yes, the ±15 hertz. Those can be early warning signs of insulation deterioration, especially, again, in systems powered by VFDs, by inverters.
So specific to VFDs often.
They seem particularly relevant there, yes. When you see those sidebands, along with signatures for winding stress and maybe stator issues, it's a strong hint the insulation is degrading. It seems small, 15 hertz, but it can be an important early flag.
And what if you can't physically connect to the ground conductor to measure?
Good point. Sometimes you can't. In that case, you can often use an inductive method. Place a special coil clamp around the ground conductor.
Like a current clamp.
Sort of, yeah, but designed for this. You measure the induced voltage. The research suggests a rough estimate, maybe 100 millivolts per amp of current. But, and this is important, you really need to compare that ground signature to the mainline current signature, especially with inverters around, because you can get a lot of electrical noise on the ground path.
Right, compare the patterns. Okay, that gives us a solid handle on how ESA and MCSA let us see these hidden electrical faults. Now, the sources also talk quite a bit about Supra Harmonics. What exactly are those?
Supra Harmonics. Okay, so these are harmonic frequencies, but in a higher range than we traditionally focused on. Specifically, the range is generally considered 2 kilohertz up to 150 kilohertz.
2 kilohertz to 150 kilohertz. That's quite high.
It is, and there's a growing focus here, mainly because of all the power electronics, the VFDs, LEDs, chargers, all that stuff in modern systems. They tend to generate noise in this range. There's even an IEC standard, 61430, that guides how to measure and analyze data up here.
Why the new focus? I thought total harmonic distortion, THD, already covered harmonics.
Common misconception. Traditional THD usually only counts harmonics up to the 50th harmonic. For a 60 Hz system, that's only 3 kilohertz.
Oh, right.
Super harmonics start at 2 kilohertz and go way beyond that 3 kilohertz limit. So standard THD measurements often completely miss the potential trouble these higher frequencies can cause. As systems get more complex with VFDs and such, we're just seeing more of this high-frequency noise.
So what kind of trouble can they cause? What are the harmful effects of superharmonics?
Oh, quite a few, unfortunately. At these higher frequencies, you get more pronounced skin effect and proximity effect in wires.
Skin effect.
Yeah. Current crowds to the surface of the conductor, increases resistance, causes localized heating, potential damage to insulation, connections.
Okay.
Plus, eddy currents in motor cores, transformer cores, they get amplified. More energy loss, more heat.
More heat. Bad for insulation.
Exactly. Superharmonics also put more voltage stress on insulation materials, increasing failure risk. They generate electromagnetic interference, EMI.
Right, interference.
They can amplify capacitive currents, maybe creating new leakage paths. They can even cause resonance in circuits, interfere with power line communication systems, and damage sensitive semiconductor components in electronics. It's a whole list.
That is a broad range of problems.
Yeah.
Any common examples of equipment that's particularly vulnerable?
Definitely. LED lighting is one. Ironically, LEDs can also cause superharmonics, but they can suffer stress on their driver circuits, shortening their life. Traditional lighting. Filament vibration, ballast stress. VFDs themselves can trip unexpectedly or have resonance issues. PLCs, the controllers for automated systems, they can get signal disturbances, operational glitches.
Oh.
And here's a really interesting one. Superharmonics can sometimes bypass shaft grounding brushes in motors.
Bypass the intended ground path.
Yeah, because at higher frequencies, the impedance changes. They might find an easier path, a lower impedance path, right through the motor bearing.
Through the bearings, what does that do?
It causes electrical discharge machining, or fluting. Basically, tiny electrical sparks erode the bearing surface. Not good.
Sounds pretty serious. Now, one source introduces this thing called the Relative Harm Index, RHI. What's that about? How does it help quantify the danger here?
Right, the RHI. It's a metric developed to better assess the potential damage from harmonics, especially these superharmonics.
Oh.
It tries to quantify the relative harm compared to the fundamental frequency, like 50 or 60 hertz. Think of it like a danger score for high-frequency electrical noise. Helps you prioritize.
A danger score. How is it calculated? What's the idea behind it?
It considers two main things: the amplitude, the dB level of the harmonic relative to the fundamental current.
Right, the dB we talked about.
Exactly, and also the actual frequency of the harmonic. The core idea is that higher frequencies tend to cause damage more quickly. So the calculation involves square the ratio of the harmonic frequency to the fundamental frequency that reflects the increased harm potential at higher frequencies combined with that dB level.
Okay, so frequency matters a lot. How do we interpret the RHI scale then? What do the numbers mean?
It's a logarithmic scale. An RHI of 0 means the potential harm is roughly the same as a similar level disturbance at the fundamental frequency.
0 is baseline harm.
Kind of, yeah. An RHI of 1 suggests about 10 times the potential harm.
10 times.
RHI of 2 is about 100 times the harm, and so on. Negative RHIs would mean less potential harm than the fundamental.
Wow, okay. The sources had some real-world examples. Can you walk through one?
Sure. There was a DFI wind turbine tower bearing example. It showed an RHI of around 3 at 5 kilohertz.
RHI of 3, so 1,000 times the harm.
Roughly, yeah. According to the scale, that's very high potential harm. Immediate attention needed. And apparently that turbine did have a history of bearing discharge issues.
Okay, that makes sense. Any other examples?
Another one involved a fan. The ground current showed an RHI over 2, up around 20 kilohertz.
RHI over 2, so 100 times harm at 20 kilohertz.
Right. Now, the actual current level might not have looked that scary on its own, but the high RHI at that high frequency pointed to a significant risk of eventual bearing failure from electrical discharge.
So RHI gives context beyond just the amplitude.
Precisely. It factors in the frequency's damaging potential.
I also saw RHI heat maps mentioned.
Yeah, that's a visualization tool. Basically a graph showing potential harm across different frequencies and amplitudes. Areas with high RHI are color-coded, usually red or orange, so analysts can quickly see where the biggest risks lie.
So practically speaking, how would a maintenance team use RHI?
Several ways. It helps pinpoint the highest risk frequency ranges for targeted diagnosis.
Focus efforts.
Right. It also lets you compare vulnerability across different components in a system. A high RHI can be strong justification for investing in harmonic filters too.
Makes the case for spending money on filtering.
Exactly. And finally, you can track RHI over time, see if things are getting worse, track degradation, and schedule maintenance proactively.
This seems super relevant for something like wind turbines, right? Complex, expensive machines. How are ESA and MCSA used there specifically?
Oh, extremely valuable in the wind sector, especially for DFIGs, doubly fed induction generators, which are a huge part of the market.
DFIGs, right.
These techniques can spot early signs of really critical failures, things like fractures in the rotor wiring.
Wiring.
It's part of the rotor winding connection. Early signs often show up as anomalies at the pole pass frequency, PPF, and signs of dynamic eccentricity rotor not perfectly centered.
Okay. Yes.
They're good for detecting bearing wear in the generator, gearbox, main bearing, gearbox faults too, even things like stator wedge loss.
Stator wedge loss.
Yeah, wedges hold the windings in place. If they loosen, it causes problems. There's a specific frequency signature for that. Involves rotor speed, stator slots, line frequency. The formula looks complex. FD SSL equals NRSSS. But the point is, a specific electrical pattern points to that mechanical issue.
Given the huge cost of turbine failures, catching these early must save a lot of money.
Oh, absolutely massive savings. Replacing a generator, gearbox, or main bearing. Hundreds of thousands of dollars, easy. Plus huge revenue loss from downtime.
Right.
If ESA or MCSA catches these issues early, often you can do less invasive, much cheaper up-tower repairs. Huge difference in downtime and cost.
Now, one source talked about nacelles circulating currents in turbines. What's that about?
Yeah. Circulating currents. These are AC currents flowing within the nacelle, the housing at the top.
Why do they happen?
Various reasons related to the generator-grid interaction. But they're bad news. They threaten the generator stator insulation, gearbox components, main bearings.
Wow.
They often cause that electrical discharge machining damage we mentioned, pitting, fluting, micro-cratering on bearing surfaces.
And these currents can be quite high, even on the ground paths.
Surprisingly high, yeah. Research found currents up to 150 amps on the main bearing ground connection in some cases.
150 amps,
Yeah.
even though the main grounding is for lightning.
Exactly. And interestingly, the frequencies of these circulating currents in the nacelle, often related to the generator's operation, can be different from the grid frequency you'd measure down at the tower base.
So are standard grounding practices like shaft brushes always enough to stop these?
Well, the findings suggest sometimes not. Conventional grounding in brushes seem to have limited success, especially against the higher frequency components, the Supra Harmonics, which love to go through bearings.
Why is that?
It comes back to impedance at different frequencies. Brushes might become less effective higher up, while the bearing's impedance might drop, offering an easier path for that damaging current.
So what's the solution? More research needed.
Exactly. There's active work on better mitigation, things like insulated bearings, insulated housings for critical parts. More solutions are expected, maybe around 2026 as the research progresses.
The sources also had a couple of case studies. What did they show?
Right. Case study 1 was a big 2,500 kilowatt dynamometer. It kept tripping.
Okay.
ESA on the power supply and MCSA on the ground both showed winding stress signatures. Turned out the stator insulation was degrading because lubricant got on it. It failed a surge test, which directly checks insulation.
So the signatures pointed to the root cause.
Pretty clearly, yeah. Case study 2 was smaller, a 746-watt motor with a known winding defect. Again, MCSA showed winding stress and stator slot signatures, correlated perfectly with the known fault confirmed by surge testing.
So it works across different scales.
Definitely illustrates the value for finding these hidden insulation weaknesses, big or small systems.
Okay, so pulling it all together, what are the main takeaways for anyone maintaining rotating machines, maybe not just wind turbines?
Well, the research strongly suggests MCSA is really effective for several common problems. Turn shorts, look for winding stress signatures, maybe stator defects appearing later,
Right.
insulation to ground degradation, watch for those line frequency plus minus 15 hertz sidebands, stator frequencies, and maybe that mirrored spectrum on the ground conductor.
Sure.
And general winding breakdown, especially with contamination or ground issues, often a combo, the plus minus 15 hertz winding stress, stator defects, and the mirrored ground current spectrum.
And this issue of high ground currents, Supra Harmonics, it's not just wind turbines, is it?
Absolutely not. The turbine examples are stark, but high ground currents and super harmonic damage. That can happen anywhere. You have VFDs, power electronics.
So industrial plants, commercial buildings.
Yeah. Same potential problems: bearing, fluting, insulation stress, electronic glitches. It's becoming a much broader issue across many sectors.
This has been really illuminating, a fantastic deep dive into a critical area for keeping machines running reliably. It's amazing how much info is hidden in those electrical fingerprints.
It really is. ESA and MCSA give us this powerful, proactive way to understand machine health. Lets us move beyond just reacting to failures and actually anticipate them.
And with power electronics everywhere now, understanding Supra Harmonics, mitigating them, it's just becoming more and more essential, isn't it?
No doubt about it. For efficiency, for reliability.
Yeah. And tools like the Relative Harm Index, RHI, seem to offer a more insightful way to gauge the real risks from these higher frequencies. Gives a more nuanced picture.
Definitely helps focus attention where it's needed most.
So as you, listening, think about the machinery in your world. Maybe it is a huge wind farm. Maybe it's a critical pump in a plant. Maybe something else entirely. Think about those hidden electrical fingerprints. They're being generated constantly. What unexpected insights might these advanced techniques reveal about their long-term health, their hidden vulnerabilities? It's definitely something worth pondering as we rely more and more on these complex electrical systems. Thanks for joining us for this deep dive.